Okay, it is being recorded right now. So as you see, ultra ambitious outline, rejection sampling, logistic regression. I want to gain actually an intuition myself of how these things work and what are they about. A logistic regression is the key to this whole NCE approach, and rejection sampling. Okay, unsupervised as supervised learning, as surprised from blast from the past, basically, and then noise contrastive estimation, and a connection at least near and dear for me is word-to-vec and negative sampling, which is practically what NCE is. So let's talk about, okay, wrong slide. Let's talk about rejection sampling. Let's talk about something that you all may know, but it's always good to recall. Remember that if we take a square, just one by one, you can see everything, right? I'm drawing there.
Yes.
Yep.
Yep.
And we'll take a circle. Well, that's my attempt on a circle. And we'll start throwing darts into the square, which are uniformly distributed in the square. Then we can estimate area of the circle, which we know. And the area of the circle will be estimated as the ratio of the number of points that hit the circle to the total number of points. We know the radius is 1, and as a side effect, we can estimate the pi number, right? Our transcendental value of pi. So this principle has been around forever. What we could do, we could also take any kind of random rectangle and any probability density that we want to sample from. And if we can generate samples uniformly distributed in this random rectangle, as long as they're uniformly distributed in the area, well, okay, I don't have the proper 1, 2, 3 algorithm described, but I should have given you the algorithm first for you to appreciate the simplicity, because the algorithm is Y. In one of the steps, there is, I'm not sure, okay, probability density. Okay, let's go with this. Remember, G is what we want to sample from, and G0 of X is what we can sample from, is this, our uniform probability. So if our sample is larger than, actually, if it would be, if it's larger of this value of Gx, we reject the sample. And then continue sampling. What it means in this picture is we keep any sample that is under the curve of your density, and we reject every sample here. Once when we're here with the samples, we only keep their X values, and we got a sample of points that were sampled from this curve, from the distribution described by this curve. And I stress it by this curve because it is insensitive to a constant factor on the curve. You can shift the curve up, down, or whatever. The as long as it's within that circle that you're throwing your darts in or uniformly sampling, the samples will conform to this distribution. So this is called rejection sampling, and that's a clever way of using samples, noise samples, uniform noise samples, right? While I'm talking it's noise contrastive estimation, right? It's a novel way to deal with unnormalized probability distributions. That's how it's claimed in 2010. This not so novel way of rejection sampling been known for, I mean, 100 years. I don't know, Buffon needle is going even back 300 years. I don't remember exactly, but it's a similar spirit. So it doesn't, like, I want to build connections in your mind. If you've seen rejection sampling, then noise contrastive estimation. Rejection sampling, in a sense, is noise contrastive estimation. You're contrasting your distribution and noise samples, distribution samples and noise samples. And by this contrast, reject or not to reject, you get to the samples that are desirable, or the ones that you were trying to generate. So that's it for rejection sampling. Then let me see. Okay, let's go with logistic regression. Totally jump to to what you already know or you think you know, but let's go in a little detail. Rogers, nod if you've seen that lecture on logistic regression. I don't know, you've skipped some and you were on some of them. Oh, okay. Let's try then. It's kind of a boring stuff, but since well, boring. No, it is amazing stuff, but it's basic. Okay, so I think this intuition of how logistic regression works is valuable here in NCE, because it's nothing but logistic regression objective function. The objective function in noise contrastive estimation. So let's try it. So blah, 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 some words. Logistic regression seeks to model the probability of an event occurring depending on the values of the independent variables, which can be categorical or numerical. Mouthful. Well, what logistic regression seeks to estimate the probability that an event occurs for a randomly selected observation versus the probability that the event doesn't occur. Logistic regression seeks to predict the effect of a series of variables on a binary response variable. Logistic regression seeks to classify observations, but by estimating the probability that an observation is in a particular category. Well, example, approved or not approved for a loan application. So what really happens is, imagine, let's look at one dimension, some parameter. Our data is coming from a bank, and we know some people have been approved for a loan, some people haven't been approved for a loan. So it's either 0 or 1. For this particular parameter, we will see something like that. And we want to classify or build a classifier, basically a predictor from this parameter, which people will be approved for a loan, which people will be rejected for a loan from that data. So, the simplest algorithm that we can use is linear classifier. But linear classifier here, or rather linear regression, right? Linear regression doesn't kind of make sense here. Linear classifier doesn't make sense either, because you only have one parameter. So how do you how do you build that predictive model? That's where that's what oh, that's what I just said. All I can do is fit lines. Imagine all we can do is linear classifier. So what people figured out back in the 50s, I forgot the name of the person, is let's try and manage our data, basically. We will, it's Richard Feynman is the famous guy for doing that. So he would do complicated calculations and proofs and everything and come up to a solution. But then he would, once he knows the solution, he would come up with intuition, which is short and quick, and then claim, okay, well, that's easy to see, right? That's the intuition. So the same here. The motivation is sort of, we have a linear classifier, or we know how to build linear decision boundaries. How can we convert our probability distribution, probability estimation problem when we only have binary data or categorical? Okay, but let's fix binary in this case. Either we won or not. So let's look at the odds ratio. So probability of winning is p plus, and probability of losing is 1 minus p plus. So we look at this ratio. Okay, we get something better than just binary, but the odds sort of are unbounded. They can have any number of values. If you look at, do you see my mouse? I hope it can be as small as you want, and it can be as large as you want. So that's not too comfortable. But we'll look if we take the log odds, then we get nice representation. Our probabilities are bounded now between 0 and 1, and everything sort of well, probabilities are between 0 and 1, but log odds now become symmetric, right? They're positive and negative and around 0. They're not like here. So those are the odds, and those are the corresponding log odds. So the scale here is sort of arbitrary and fastly changing, and the scale here is more well behaved. So, okay. That was my example from the capacitor, when people have wrong idea and still arrive at the right answer. It's my intuition about logistic regression, which is actually a classifier in all respects, but it's, people still call it logistic regression. So the same thing with electricity story here. I don't know if we have time or we can skip it. Let's skip it. So once we have log odds, we can fit those log odds by a linear function. So we say, okay, our log odds go from negative values through 0 to positive values. They kind of nicely centered around 0, and we can model the log odds with linear decision boundary, or linear estimation. Once we do that, we can observe that, well, in a multi-class situation, log odds, say we have classes from 1 through k, and then in a 2-class, in a binary, it's easy, right? There are only 2 classes, the positive class and then 1 minus the degrees of freedom. In a multi-class situation, we arbitrarily pick a class k. It's absolutely arbitrary. Doesn't mean, you know, doesn't have to be anything. And then we look at the log ratio of all of the classes with respect to the class k, and model this as linear linear decision boundary, linear combination, linear weighted sum of the input. For class A, for class K, we just assume that our log odds is 0, is 1. You'll see what happens. So when we model our log odds as a linear combination, weighted linear sum, we can reconstruct and solve for p plus for the probability. And our probability, if you follow through the step, turns out to be the logistic sigmoid function. And we arrived at logistic sigmoid from trying to feed log odds with a linear function. That's why I'm bringing it up. I want to stress it here. And those are the same, just some transformation. And in a multi-class situation, for class K, the probability for any of the K from 1 through K minus 1, probability of the class given an observation is modeled as this ratio, e to the linear transformation of x, 1 plus the sum of all of the other classes, basically. Those are the other classes. This 1 is also the class. For probability of class K, we model e to the w transpose x as 1, or assign rather. That was our decision. This one and this one and this one are the same. We're just saying unnormalized value for class K, which we excluded from the rest, is 1. The normalization will take care of it. So an interesting observation. So what does this remind you about? If this is 0, then e to the 0 is 1, right? So we just forcefully assign w to zeros. But this whole thing is nothing but softmax. There's nothing but softmax function. So our neural networks that do multi-class classification, more than one, they're actually doing logistic regression or learning a kernel for logistic regression at the that happens at the end of the network. Okay, this is interesting. I think that comes from Bishop's book. So what's posterior probability of class 1 given a sample X in two-class situation? In two-class situation, it's this basically. It's the likelihood times the prior and divided by the evidence, right? So let's introduce A, just do some algebraic transformation. If we introduce A as log ratio of our posteriors, because look at this, when we divide this posterior by, well, when we divide, well, the normalizing factors cancel out because it's the same normalizing factor. We get this ratio. So this is our decision boundary likelihood ratio or posterior ratio and the log of it. When we introduce this quantity A and plug it into this equation, we arrive at sigmoid. And our sigmoid function now is, well, it's a logistic sigmoid with respect to A, with respect to the ratio of posteriors. And, you know, like the log ratio, log is a monotonic function. It's the same as the ratio, right? When the ratio changes above 1, it is class 1. When it is below 1, it is class 2. But for log, it is 0 is the cutting point, right? Because when it's 1, log is 0. When it's negative, that means class 2. When it's positive, that means class 1. The surprising part here that we started with when we were talking about log odds, we assumed a functional form of our distribution. We assumed that we're modeling our log odds with linear function, with linear combination of the weights in the feature weights. here, we didn't make any assumptions about any of the probability distributions, and we arrived at, this is kind of aside, but still a curious aside, that our posterior, class posterior, can be modeled as a sigmoid, logistic sigmoid of our decision boundary or likelihood ratio. Logistic sigmoid, besides that it just pops up in the posterior for classes, has nice properties, like derivative can be expressed in terms of itself, the logistic sigmoid as well, and so on and so forth. What we're after before the NCE, before the noise contrastive estimation, is the likelihood, maximizing likelihood. So maximum likelihood estimate for a two-class problem. So this is just a general formulation for any number of classes, any number of observations. Those are observations. We assume, as usual, IID and all of the classes. When we have just two classes, our probability of coming from one class, like it either comes from one class or another. So we split this product in two. And then we know that when it comes from class one, our probability distribution is modeled by logistic sigmoid. But when it comes from class two, it's modeled by 1 minus logistic sigmoid. That's how we set it in the beginning. So this is nothing but like now to model in like this is written in such a way that we know what class X is coming from. Like when we know, we're saying, okay, when X is coming from C1, it is here. When it's coming from C2, it's there. But we can write exactly the same knowledge, encode the same knowledge in this power because this label is either 1, and when label is 1, then sigma is selected. This goes to 1. Well, the power goes to 0, and this expression goes to 1. When label is 0, this becomes 1, and we're dealing with probability distribution probability distribution of class 2. When okay, now we need, I don't have if you can open the paper, the link, equation 3. Look at equation 3 in the paper, and look here at this expression, likelihood of well, it's equation 3 and equation 11. You can see that noise contrastive estimation and is nothing but objective, or what are they called? Objective function of NCE is just objective function of logistic regression. It's just a logistic regression between samples that come from noise, and we know when they come from noise, right? We have the label, and samples because we generate the noise, and the samples when they come from the distribution of interest. Why does it work? What do I have there? Nice.
Can I ask a question?
You better, because otherwise I'm just...
So the functions in the paper are evaluated over the different data. There's X and there's Y. Does that, I mean, that doesn't match the equation you showed in the slide. Is that a problem, or how?
It matches perfectly. Rogers, come on. In the paper, Y is your noise. So all that means is, oh, you get Y, you plug it here. You get X, you plug it here. If you go back here, it is like deciding what it is evaluated. It is the same X, but when you see that your X is called Y, that means your label is 0, or when it's just a label. They encode the label in the name, X versus Y. But it's just. But yeah, that's my understanding, right? That whatever I could quickly gain, like, was it clear so far? Like, I'm trying to build an intuition of why did that thing work? Okay, but now back to rejection sampling and being kind of surprised by the claims of that paper. I mean, we always keep going in circles and we hope it's a spiral, right? In their 2009 second edition, I will copy from the book now, second edition, because I didn't, slides very expensive to prepare. Alex, you get kudos and whatever medal for putting slides together. For me, it's a lot of work. So second edition, Hasty, Tepshirani, Friedman book, The Elements of Statistical Learning. Section 14.2.4. I didn't have time to check if this section was there in the first edition as well. But what they say is, imagine that you have data set x1 and xn that comes from g of x. And then you have another data set that you sample. Well, it's also x1, some other x1 through n0, right? That you sample from a noise source, whatever distribution. The only condition is you have to be able to sample from this. And this you already have, or the world gives it to you and you want to estimate this distribution. So we can combine those samples, not an algebraic sum, but we can combine those samples by carefully weighting them and then, in effect, we will have samples from this distribution. So we'll just throw the samples together, the ones that we sample and the ones that we got that we're interested in. Then, what is the probability? Oh, well, now we have, this is a different Y, Rogers. It's not the Y that was there in the, they're all X's, but we have a label and a sample. And our label is either 1 or 0, depending on where it comes from. So we want to write down the probability of Y given X. And just using Bayesian theorem, basically. It either comes from here or here. That we don't have the priors. This is the full joint. That's why this form, right? And then you can even write it like the ratio that we already saw. Remember, this is before NCE paper. I mean, way before if it was in the first edition. Once we have this, let's call, they call it for some reason they call it mu. Maybe I'm missing something. I don't understand if it's the mean. If you can clearly see that it's the mean of something, then okay. But the claim is we can estimate this mu, since this is our logistic function of posterior ratio. We can estimate this by as a classifier, as logistic regression classifier. And once we estimated mu, we can look at these two parts and recognize that our estimate of G and I'm cheating, I'm looking into the book. So what they're saying is, in general, let me change the color instead of changing the page. In general, if we can estimate log ratio of G0 of X to G0, look, logistic regression. If we can estimate the log odds as a function here, which is just estimating the difference whether the sample comes from G0 or G, or not the difference, like building a classifier basically, logistic regression of classifier for samples coming from noise, contrast to noise. Oh yes, Rogers, you will like it. Then what it comes down to, our estimate of Gx is nothing but G0 of X times e to the f of X. This f of X is our estimation of is our classifier, basically our decision boundary, or log odds, which we estimate through logistic regression, log odds. And this also doesn't require any knowledge of the weight normalizing partition function. But interestingly, so what they say, interestingly to us, is that this ratio is the contrast function between two distributions. And if, for example, now when you can model this, you can model any distribution, or as long as you can put a contrast function to it. So for example, for independence, your contrast function, G0 of X, is the product of G0 of X sub I of independent components. And you can sample from this function by randomly permuting the order of features every time you sample. So your features are always randomly reordered at every X. That is like you destroy all of the possible relationship with them. So back to Common and his noise, his contrast functions for ICA. So this is important phrase. Although this approach of transforming the problem to one of supervised learning seems to have been part of the statistics folklore for some time, it doesn't appear to have had much impact despite its potential to bring well-developed supervised learning methodology to bear on unsupervised learning problems. One reason may be that the problem must be enlarged with a simulated data set generated by Monte Carlo techniques, since the size of this data set could be or should be at least as large as the data sample. The computation and memory requirements of the estimation procedure are at least doubled. I am totally puzzled at this because it doesn't make sense. We've been doing Monte Carlo simulations since, 50s, 48, I think, when it was discovered by Ulam and all those guys. But
so
it's interesting.
the statement is from the book or the paper?
No, from the book.
Okay.
Which was before the paper. And I was surprised to discover this. But basically, for this section in the paper, 14.2.4, describes exactly what has been proposed in NCE by Gutman and Huverinen, noise contrastive estimation. And they describe it as, in 2 pages, oh, 3 actually, very quickly, as well-known folklore, with also a surprise of why didn't it work. So if we pull, I didn't go in depth into the paper itself because they actually don't, well, that was the paper. The logistic regression is their section 2.2. But now our logistic regression between 2 classes. One class is random sample class, and another class is the sample from your distribution that you're trying to model or you're trying to estimate. And their functional form is basically, now maybe it's worth putting out the board. Obviously I need much better lecture if I were to teach this, but I wanted to understand this rather as part of the lecture, our reading group series. Just parameterized. Basically, this is the logistic regression objective function. Okay, they call it Y, of course, because when that's how they notation, but it's practically the same. So J, blah blah blah. Objective, you want to find the parameters, and H function with some input U is our logistic sigmoid. G of U. The parameters are of G. In the end, those parameters just trickle down to G. And G of U is the log odds. Look, in the paper, somehow, well, I mean, it's their choice, but it's not the most intuitive thing for me. I have to pause for a second. Why do I have to pause for a second? I don't know. Like, couldn't they just write it like that? N is noise. So we have log ratio, log odds basically from logistic regression, and G is modeling those log odds with theta. Yes, it's the generalized logistic regression of the element of statistical learning book, where this is our f of x function. It doesn't have to be linear, and it doesn't have to be linear either here. So then they go through the proof that it's consistent and unbiased estimator. Oh, I actually, I don't know if they prove that it's unbiased. They prove consistency. What I wanted to talk about, and I don't have time, is word to vec, because when Nikolov et al., the team, published word to vec paper, they had 2 models there. Continuous bag of words. Continuous bag of words says, okay, we have neighborhood of a word, so the words next to it, and we want to predict that word. Like, let's train our model to predict that word correctly from its neighborhood. The bag of words model, continuous bag of words model, is because you start with modeling your dictionary as a one-hot encoding. And basically, when you have the neighborhood, your neighborhood is nothing but not a count even vector, but just inclusion vector, zeros and ones. And so it is a bag of words, but then you train it as a continuous. But another one was skipgram model. And skipgram was the reverse. We have a word, and we want to predict each element in the neighborhood. That was easy in a sense, but inefficient, because you had to go through all of the yeah, like we really need to go into detail if we want to understand, but you needed to normalize with respect to the full vocabulary, full dictionary, in order to do that in softmax. And funnily, in the same year, 2013, I'm almost done. In the same year, 2013, at the same conference, NIPS 2013, two papers come out from Mnih and Kavuchagli from DeepMind, and from Mikalev. I don't remember if he was still at Google or Facebook. So what the Mnih and Kavuchagli introduced, they said, okay, let's use noise contrastive estimation of Gutmann. That's the first paper that I threw there. And instead of optimizing over all possible things, just use the noise words that are not within the neighborhood. What Mikalev introduced is called negative sampling, which is essentially the same with some differences in normalization, and so different theoretical guarantees. The noise contrastive estimation is a general approach. And as I hope I conveyed to you now, that it's been used or known in the field forever. But this is a general approach to modeling density functions. It's a general approach of using supervised learning algorithms for modeling density functions. Let's put it that way. Negative sampling is correct approach, very efficient, but it is only very specific and only works for word to vec. So I thought if we were to go through that into that details, that would be a curious also thing. And Usman prepared some slides on contrastive predictive coding, but we don't have time. Sorry, Usman. Maybe we can go through it next time, or maybe we'll somehow.
Yeah, next time. Okay.
Yeah, decide with Alex. Okay, I hope I scratched the surface on this. It's very easy to go through just equations of the paper and say, okay, here's what is done on the surface. But I think what they're actually doing, well, I've tried to convey or recover of what they're actually doing. Any questions, discussions before we conclude?
Not for me, thanks though.
Okay, done. Thank you. Next time, I think, Alex, your turn, or we'll go with Usman as CPC.
I think you can go ahead, but like I need some more time. I'm kind of digging into variational encoders and trying to understand like how you can play around with them.
Well, I'm interested in this energy. Your classifier, the paper, your classifier is secretly an energy-based model. I suggest that paper for next time then, if we can.
I mean, I can start on it. I think there are like a couple of papers. So like I'm currently just building reading list for it.
Oh, okay. Oh, okay. So you don't want to go into that yet. You want to first.
I think I saw some works from Huvarian about energy-based models. But I will see. I will let you know.
Okay.
by the middle of next week, maybe earlier.
Okay. I gotta run now. Thanks everyone. I'll put everything on YouTube, and I will share in the channel the link.
Thanks, Sergey.
Thank you. Bye.
Thanks.